This is objective 4b and 5b. So it is just the integral side of our base A and base E. So we already know the derivative patterns. So now we just need to work backwards. And so just a little reminder. So if I wanted to know what the derivative of e to the u was, I would say that it's just e to the u again. And then because of chain rule times the derivative of the power. So we're just kind of working backwards. And so that's what this left side is all about. So we're trying to find the antiderivative of e to the u. And that would just be e to the u plus c. So the important component here, though, is that u is our function of x. And so we're going to always have to do kind of a chain rule component, like what is that u to u. And then on the a to the u pattern, so just a reminder of that derivative. So that derivative is a to the u, and then times the derivative of the exponent, so u prime, but then multiplied by the natural log of a. So that's the derivative. So the difference now for integration is instead of multiplying by ln of a, we're going to actually divide by it. Okay, so watch out for that. All right, so let's go ahead and take a look at a couple of these problems here. And so the first thing is always, try to rewrite it in that format of, where you're going to have your E, you're basing to U, and then your remaining terms after it. Okay, so, and that will hopefully work out to be that du. And then if there's a coefficient, of course, we will pull that out. So we have an e to the u pattern, okay, so which the answer is not just going to be e to the 2x plus 1. We need to know that, okay, u is equal to 2x plus 1. And then we have to calculate the derivative. So the derivative of 2x plus 1 is 2, and then multiply that dx over. So I only have a dx here, so that means I'm going to divide both sides by 2. Okay, so then let's go ahead and set that in a e to the u piece together. So I will have replace 2x plus 1 with u, right, because we're getting it from here. And then we're going to replace the dx with du divided by 2. And I'm going to do the divided by 2 out to the front. So now it looks like our pattern from above. So the integral of e to the u is just e to the u, but don't forget the 1/2, and then plus our constant. And so then when we do our last substitution, we will have e to the 2x plus 1 and then plus c. Okay, so the piece that most people tend to forget is that we always have to do a u to u for every kind of exponential that we have. All right, so let's go ahead and take a look at the next one. So for that one there, we're going to let u equal our power, which is 3x. And then we're going to take that derivative, which is just 3, and then dx. And then divide both sides by 3 so that we get just the dx component. And then now we're going to go ahead and do our substitution. So I'll have the integral of e, and then replace the 3x with u. And then dx is going to replace with du over 3. And then instead of over 3, I'm going to pull the 1/3 out to the front. And then now we have that perfect little pattern for number 1. So then that integral would be 1/3 and then e to the u plus c, and then substitute u with our 3x, and so we would have that. Okay, so pretty easy as long as we're always following that kind of pattern. So then, of course, they get trickier because that's what we always do, make it a little trickier. So we do have a fraction. So whenever we have a fraction, we always want to pull up that into the front. So I'm going to rewrite that as e to the negative x, because I'm going to move it up. Oops, that should be a 2. Make that a 2x. Plus 2e to the x plus 3, and then dx. So because this is just a monomial, I'm going to go ahead and just distribute that in to simplify this. So that will give me negative 1x plus 2x, so I add my powers. And then negative x plus x is 0, and then finally 3e to the negative x, and all of that with respect to dx. So I have all of these different terms, so not because I have to, but just because it's going to make it a little easier for me to explain, is I'm going to go ahead and split this up into 3 different formats, or 3 different integrals. So I have e to the x dx, and then e to the 0 is just 1, so 2 times 1 is 2. And 3 e to the negative x, and then dx. So I can split it because it's adding, right? Addition and subtraction I can separate. So right here, this e to the x dx, I could choose to say, okay, let's let u equal x, and then du is equal to dx. But then all I'm doing is really changing the variables, so I don't need to do any adjusting. So I'm just going to treat this as already in the e to the u du format. And so that integral will just be e to the x. And then on the integral of 2 with respect to x, that would be 2x. And then on this one, I'm going to pull the 3 out. And then because this is not just a regular x, then I'm going to go ahead and do my u to u. And again, those of you who do this in your head, perfect. So I would let u equal negative x, and then du equals negative 1 dx, and then divide by negative 1. And so then when I do that, I'm going to go ahead and move that negative 1 out to the front. So that will actually be a negative 3 here. And then I will have e to the u du. And then now I can follow the pattern from above. So I still have e to the x. I still have a 2x. I still have that negative 3. I guess that could be a minus. And then the integral of e to the u du. So if I look at the pattern above, that would just be e to the u and then plus c. And then for my last step, I'm going to go ahead and make that a minus now. Replace the u back into that negative x. And that would be my answer. Okay. All right. So number 4. So we have a denominator. So what do? Every single time we see that denominator, we pull it up to the top. Do not make those powers opposite because it's that quantity that's to the negative 1. So then once I have that, I'm really, even though it looks like I have 2 groupings, that second one is only to a power of 1. So really my u has to be that first one, right? Because it's to the negative 1 power. And so that kind of makes it a lot easier, right? So I'm going to let u equal e to the x plus e to the negative x. So again, I'm choosing this one right here to be my u term because it's to a negative 1 power, while this is to a power of 1. And I can't distribute or do anything here because it's that addition with a power, so that just makes it kind of stuck. So let's go ahead and take that derivative. So the derivative of e to the x is e to the x, and then times the derivative of x, which is 1. And then I have plus, and then e to the negative x times the derivative of negative x is negative 1. And then I should have a dx there, but I'll write that on the next line. So I'm going to go ahead and simplify this just a little bit. So that would be e to the x, and then minus, because I have that positive negative there, e to the negative x, and then I'm going to go ahead and smush my dx in. And so if you see, like, these line up perfectly, right? As well as they should, right? Or maybe not perfectly, because like maybe I'll have a times 2 or a times 3 or whatever I have to contend with. But in general, though, it should always work out nicely, right? Because we are not at that level yet where we can integrate not nice. Okay? So we're still in the nice phase. All right, so let's go into our substitution. So this first portion was my u term, and then all of this matched up perfectly to be my du. So then I would have the integral of u to the negative 1 and then du. And then I know that integral is the natural log of the absolute value of u plus c. So that's from the last objective. And then go ahead and replace that u back in terms of x. So e to the x plus e to the negative x plus c. And then I cannot simplify that at all because I have that natural log, right? So because I have that natural log, or because I have that addition with that natural log, that's keeping me from doing all of that, right? All right, so let's go ahead and take a look at the next couple here. So we'll look at 5 and 6, back into draw mode. Get back into draw mode. There we go. All right, so I'm going to go ahead and do a little rearranging here because I want my a to the u first. So that would be 7x squared, and then my remaining terms after. And again, because I'm trying to get it into that format, right? So the format of that kind of a to the u, du, making sure we're getting into that, right? So that was a to the u du. So I want a to the u first, and then all my remaining terms last. So here, so my u is the power. So u is the power, and I'm knowing that because of the pattern here. And then I want to calculate the derivative. So that would be 2x to the first dx. And I have just an x dx, so that means I'm going to go ahead and divide by 2. And so then once I get to here, I'm going to go ahead and do my substitution. So the 7 stays a 7. That doesn't turn into something different. X squared replaces with u. And then x dx is that du over 2, but the over 2 out to the front. And then now I'm going to follow the pattern, right? So the pattern that was at the top of the notes. So I have the 1/2, which is my coefficient, and the pattern was a to the u divided by the natural log of the base, which was 7. So then this is going to be 7 to the u, and u is x squared. And then this is 1/2 times that, so I'm going to go ahead and just multiply those two together. So that would be 2 times the natural log of 7, and then plus c. And then I'm going to do a little trickery here. I'm going to pull that 2 up and make it a power. And that is from your log property days. So 7 squared, which is 49. So, oops, that says 7x squared. Not what I meant, people. Okay, so I meant 7 to the power of x squared is what I meant. And there we go. All right, let's do another one, right? Because we can't have enough fun. All right, so we have a denominator, so I'm going to yank it to the top, right? Try to be consistent with that, yeah? And then times 4 to the power of x dx. So the only grouping I have, so it's not going to fit that a to the u pattern because that was like a style like that. So I have a grouping here. So I'm going to go ahead and let u equal what's inside that -1 power, which is 4 to the x, and then plus 1. So now I want to take the derivative. So this is derivative a to the u pattern. So that would be a to the u times the derivative of the power times the natural log of the base. So that's the derivative, right? I don't want to confuse that with the integral pattern. And so now if I look over here, I have a 4 to the x dx, but not that natural log of 4. So I'm going to divide that over to make it look like what I actually had. All right, so let's do a substitution. So 4 to the x plus 1 is u, and then I have that power of -1. And then 4 to the x dx is going to swap out for du over the ln of 4, but I'm going to move that out to the front. Okay, so I can't do power rule, but I know that u to the -1 is just the natural log of the absolute value of u, and then plus c. And then I'm going to go ahead and do that substitution. And then I'm going to go ahead and make this one fraction. So that would be the natural log of the absolute value of 4 to the x plus 1, all divided by the natural log of 4, and then plus c. Okay, so far, so good. But these are tricky, right? These can be tricky. All right, so now we're going to mix it up a little bit, and we're going to go into, sorry, I'm checking out what I got going on there. Okay, 7 and 8, so our last two. And for these two right here, we're going to do definite integrals. So definite integrals are when we have the limits on there. All right, so first thing I always want to do, I got this little denominator guy going on here. So I am going to look at that, though, just a little different than I have been saying. Like I would be like, oh, make that to the -1 power, right? Like that's what I've been kind of saying all along. Like, hey, pull it up. So, but like if I look at that cosine squared to the -1, that's the same as 1 over cosine squared. And that, my friends, what is that definition? Yeah, secant squared. Okay. So that's actually the way I want to think about it, mostly because I think it'll just look cleaner. And then I won't be thinking like it's a grouping of a normal, -1 type of style. And that's why I'm going to avoid that, because otherwise this might be a little like, wait, what's my grouping? Okay, so 1 over cosine squared, right, is just secant squared. And so that kind of helps me out with like thinking about, okay, what should I let equal what? All right, so I know that I have e to the tangent x, so I'm going to be looking at that whole e to the u du pattern. And so I'm going to let u equal tangent, and then its derivative is, oh my gravy, secant squared x dx. Hey, look how perfect that is. All right, so let's go ahead and do my substitution. So when I do that, I will have the integral of e to the u, and then that's perfect, right, du. And then I need to switch out my limits, so don't I? So let's go with at x equals pi over 3. So that would be tangent of pi over 3, which is 60 degrees. This is going to take me a second. Root 3 over 1, so root 3. I hope I did that right. Don't tell me if I didn't. All right, and then at x equals pi over 4. And so that would be tangent of pi over 4, and that would just be 1. So then I'm going from 1 to root 3. And so let's go ahead and integrate that. So the integral of e to the u is e to the u. And then change your notation from 1 to root 3. And then f of b minus f of a. So that would be e to the root 3 minus e to the 1. And then just leave it like that. No decimals needed. All right, let's do our last one, number 8. Okay, so 5 to the negative x dx. So I'm going to let u equal, no rearranging needed, yeah? So u will equal my negative x, and then I will take that derivative, which is negative 1 dx. So lovely. And then divide by negative 1. So what will that give me? So I'm going to work over here so I'm not smishing over there. So then I will have 5 to the u, and then du over negative 1, but I'm going to pull that negative out. And then I'm going to swap out my limits of x and make them into limits of u. So at x is equal to 1, u would equal negative 1. And then at x equals 0, my lower limit, u would equal negative 0, which is just 0. All right, so the integral of 5 to the u. So 5 to the u is 5 to the u divided by ln of the base. And we're going from 0 to negative 1 and carry that negative down. And then substitute in negative 1. So that would be 5 to the negative 1 over natural log of 5 minus 5 to the 0 over the natural log of 5. And then I could do some fancy stuff if I wanted to. Should I do some fancy stuff? Nah, we'll call that good. But 5 to the 0 is 1. And that is the end of that.